Hey, math people. So no camera. I just recently shaved my beard and I'm very self-conscious about it. Moving onward, moving forward. Stop talking about that now. Cool. I'm playing this game right now, TFT. This is what I'm playing to pass the time in between prepping for calculus. That's actually how I started my morning. I was doing work for calculus, which is why I haven't been posting a lot of videos. It's a lot of work, and I got kind of sidetracked in another mathematical thought on this game. Let me explain the very fun and insightful math on this. I think this video is going to be a little long, but there's a pretty big revelation at the end, I think, if you're a fan of combinations, permutations, all those kind of discrete math topics. So this video assumes that you're pretty good at factorial logic and you know what those other two things are, combinations. If you don't know anything like 3 choose 2, if that doesn't sound familiar to you, or 7 choose 4, then in here I'll even show you the notation, I guess. I don't know. So if you don't know this this notation, then sometimes it's written like this, though. Then this might not be for you, but maybe you might learn something from it if you don't know that kind of stuff. Anyway, I'm going to go back to my mouse real fast. In this game, TFT, you can make items on your, what are essentially like chess pieces on a board. And the way you make an item, so let's just say I wanted to make this Hex-Tech Gunblade, I would need to combine two sub-items. I would need to combine this sword and this, it's a rod, it's like a staff for mages. Together, they create Hex-Tech Gunblade. Cool. So a friend of mine who just recently got into the game, he said, well, how many items are in the game? He counted the number of sub-items, 1, 2, 3, 4, 5, 6, 7, 8, 9. Said, oh, okay, 9 times 9. There are 81 combinations in the game. Intuitively, that sounds kind of right, but in practice, it's very wrong. There's not 81 items in the game. You can actually see really clearly here that there's a lot of repeats in this chart. We have Infinity Edge listed twice, and that's because the order doesn't matter in which you combine them. Combining this, what's called BF Sword, with this knuckle item creates Infinity Edge. Doesn't matter which item you put on your hero first. No matter what, it creates Infinity Edge. So how many items are there truly in this game? Let's do some math. Taking out my handy calculator, although I'm probably going to reference back to this in a second. Let's look at the first row. If I just look at the total number of knuckle combinations, which is a new item to the game, by the way, so adding a new item does something to this formula we're going to find, and I'll talk about that momentarily, I guess. Right now, I have 9 different combinations of items with just knuckles. 1, 2, 3, 4, 5, 6, 7, 8, 9. The moment I get to this sword, it looks like I have 9 as well. However, the repeat, right? This Infinity Edge is repeated twice. The other 8 are unique, though. So I have 8 unique items the moment I start the next row. Now, if I go down to this rod, all of a sudden I have less unique item combinations because I see that this jeweled gauntlet is already up here, and it's down here repeated again. Likewise, Hex-Tech Gunblade is also repeated, so all these items thereafter, 1, 2, 3, 4, 5, 6, 7, are unique. Hopefully we're seeing a pattern here. 9, 8, 7, here we're going to have 6, 5, 4, 3, 2, 1. By the time you get down here, you have only one unique item choice, and it's force of nature. So mathematically what's going on here, we have 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1, and that was tedious, 45 new items. So before Knuckles, they had only 36 items. I encourage you to think about why that makes sense, because this was the 9th item. The moment you added this 9, you have 45. If I take away that 9, I have 36. So these are actually famous numbers. 1 plus 2, well, 1 is famous, obviously. 1 plus 2 is 3. 3 is also a pretty famous number. Plus 3 is 6, that's famous. Plus 4, that's 10, that's famous too. These are called triangular numbers. They create a triangle. So I made a video on this a while back called bowling math or something like that. So let's just say you have bowling pins, right? If you have 1 row, you got 1 pin. You got 2 rows, you got 3 pins. You got 3 rows, you got, math, 6 pins. You got 4 rows, you got 10 pins. And this is the standard setup for bowling pins, right? There's 10. So these are called triangular numbers. Here, I'm not going to write this down. It's going to be sloppy. I'll just go to Wikipedia. Yeah, triangular numbers. So there's a fancy formula for it, and it's right here. So in our game right now, we have, well, let's not worry about this all too much. I want to get to that, but I actually want to talk about this first. Combinations. To me, when I was thinking about how many items there were in this game, I don't know, I was on like my 7th hour in a row of playing this, so I really wasn't in a state of mind to do math. I was like, well, it's got to be some sort of choose function. I have 9 choices, 9 choose 2. That's got to be it. So I have a calculator for this. How about we use it? 9 choose 2. 36. Well, shoot, that's not it. I don't know. What if I just added 1 to that? 10 choose 2. Would that do anything? It does. It works, but why does it work? That's weird. So I thought about it. I went back, and I was thinking, well, wait a minute. This idea of replacement and without replacement is really important. 36 is a great number. 36 is representative of the number of items in the game where you do not replace. So for example, we have double knuckles here. So together you can make an item there. You can replace the knuckles. You can put it back in the bin. You can combine these. You end up getting this, whatever it's called, Thieves' Glove. And there are actually 9 of these in the game, if I can math right. Yeah, 9. 1, 2, 3. It's actually on all the diagonals. 4, 5, 6, 7, 8, 9. All these guys need to be considered. So 36 plus 9 is that 45. This is actually combinations with replacement. And this is not commonly, at least I don't think so, taught in high school, this formula compared to this guy. Usually we just teach this guy. But it's actually the same thought, except you can replace. So 9 choose 2, you should get 45. Sure enough, you do. So this is really interesting. I see all these numbers that are seemingly intertwined together through these formulas, and I feel like there's many different mathematical ways of representing the number of combinations here via combination logic. And that's what I want to show you today, is that there are. So the first way that I kind of pseudo-discovered just by playing around with it is I added 1 to the number of objects in total, and I did 10 choose 2, and I got that 45 value. The other way was I used the combination with replacement, and I said, well, okay, 9 choose 2 with replacement. I don't have to do any additional math. It's just 45. The other outlet I took was I just did 9 choose 2, and I had 36, and I said, well, you have these 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. You have these 9 additional items, and I just said, well, why can't you just simply add 36 to that? 36 plus 9 is 45. You can, is the answer to that. You can. This will just always work. So to kind of, I guess, break down the with replacement without replacement idea a little bit further, because I can understand how that could be confusing. Let's just pretend I had only 3 items, 1, 2, and 3. So I want to do combinations with replacement, and I want to do combinations without replacement. Let's do without replacement first. This is more common in high school. So how many different combinations can you have? And we're going to choose 2. So we're going to do 3 choose 2. That's what we're going to be playing around with right now. And with replacement, it looks like a notation for it would be to use a subscript with a capital R. So I want to talk about kind of the intuition behind why these two things are different. So 3 choose 2. I just want to choose 2 items here. That's it. So let's just say I choose item number 1 first. I can choose 2 along with that. I can also choose 1 and 3. And that's it. Those are my only combinations where I choose 1. Let's say I chose 2 first. If I went to choose 1, I've already chosen 1 before. Order here does not matter with combinations. So if you think back to the video game example that I'm doing, you can attach sword with gauntlet or gauntlet with sword. You get the same item either way. So 2 and 1 does not matter. It doesn't count as a unique choice, rather. So 2, the only other combination that 2 has not met up with is 3. 2 and 3. If I try to do 3, 3 is already matched with 1, and it's already matched with 2, so I really just can't do anything else with this. In total, there are 3 combinations. 3 combos. Now, what if I did with replacement? How is this going to change my 3 choices? Well, firstly, we can start with 1 and 2. And we can also do 1 and 3. However, the new combination is 1 and 1. I can choose 1, I can replace it, I can put it back, and I can choose 1 again. So this is the kind of new idea behind this. So let's just continue with this pattern, right? I can do 2 and 3 like I could before, but I can also do 2 and 2. Lastly here, we can consider our final piece 3. Before, it didn't match with 1, or sorry, it already matched with 1, and it already matched with 2, but now we can do 3 and 3. That is the other combination here. Interesting shape is developing. I have 1, 2, 3, 4, 5, 6. I have 6 combinations. Okay, so going back to the TFT example here, I deduced that 3 possible ideas are the same thing. I said that using the replacement calculator, 9 choose 2 got me 45. I said using the normal without replacement calculator, 10 choose 2 got me 45. And I also said that 9 choose 2, if we add 9 to that, so if we add the number of objects to that n, we end up getting 45 as well. So those are 3 different lines of thought. Okay, so my conjecture here is that all 3 ideas are the same. I want to prove that to you mathematically. I could use a tool called induction for this, but I feel like this is going to be a better way. I wanted to use the formulas. I want to go back to these combination formulas here. We can see that there's an n choose r formula. This is the one without replacement, and there's also one with replacement. I want to use both of these guys. So I'm just going to copy them down real fast. So now let us use these 2 formulas with the 3 different approaches I was talking about. How about we do the one with replacement last? So I will say n choose 2 with replacement. This one I will prove last. This is the least common to use of the 3, so it makes sense to use it at the end here. Note what I'm doing here. I'm always choosing 2. So in this game TFT, it's always 2 sub-items to make 1 larger item, so this will remain a constant 2. I did n here instead of 9 though, and this is to allow room for growth. What if they decided to add another item to make it 10, or 2 more items, right, to make it 11? So in which case it would be 11 choose 2, or 10 choose 2 with replacement. So with that said, I'm going to leave this generally as n, and actually it's going to be a very nice result at the end, so you'll see there's a little bit of motivation for why I'm keeping it n here. The other 2 are going to have no replacement. So the first route that I told you about was n plus 1 choose 2. If you recall here, and I'll go back to the pages here, 10 choose 2 using our without replacement formula was 45. That is the same as 9 choose 2 with replacement. I can do one more just to further prove it, right? 11 choose 2 is 55. With replacement, 10 choose 2 is also 55. So if we simply add 1, we end up getting the same result. I'm saying that these 2 are the same. That is what I'm saying. So then for the final route, I did not use replacement. I just simply used n choose 2, and I added those diagonals, if you remember. So just to refresh, I did 9 choose 2 to get 36, and I said, oh, well, this is just barely off. What if I added the total number of objects to it, right? It was that diagonal. I missed all these double knuckles or double swords or double rods here. I added 9. I added the total number of objects here to n choose 2. So the total number of objects is generally n. So that's exactly what I'm going to do. I'm going to take n choose 2, and I'm going to add n to it. I'm going to put the n up front though. So I want to add n to n choose 2. I'm saying all 3 of these things are the same. Let's do this. So by definition, the first one's the easiest. I'm going to say this is equal to, I'm going to rewrite this n here. By definition, n choose 2, I just want to plug this into the formula. I want to plug it into this guy down here. So I'm going to do exactly that. N here is still n, so no simplification needs to be done. And in this world here, r is now 2, so I'm going to write 2 factorial. And then now we have n minus r, so this will be n minus 2 factorial. So I want to pretty this up. This is a very ugly looking expression right now. So some really quick side math here. The way permutations work. If I had like something like 5 factorial, this is the same thing as 5 times 4 times 3 times 2 times 1. So 4 factorial would be 4 times 3 times 2 times 1. A nice little trick with factorial is that nothing was stopping me from stopping this chain earlier. I could have said 5 factorial is the same thing as 5 times 4 times 3. And I could have stopped it there. I could have just said times 3 factorial, because I know 3 factorial is 3 times 2 times 1. So I can stop this multiplication chain anytime I want. So generally, if I wanted to write, say, n factorial, I would write this as, well, n times, well, I took away 1 to get from 5 to 4. I can take away 1 here. N minus 1 times, I'll take away 1 again, n minus 2, so on and so forth. Let's just say, I can see I'm running off the board here. Let's just say I wanted to end it there, though. Let's just say that I really wanted to stop on n minus 2. Maybe that's very practical for me to stop at. So I'm going to do n minus 2, and there's a little factorial right at the end there. I can see I'm cutting off the screen. But you can end it there, or you can keep going. You can do n times n minus 1 times n minus 2 times n minus 3 times n minus 4. It just matters how many items you have at that point, how many objects you have. Anyways, I'm going to use this logic here to my advantage in the simplification of this problem. So I'm going to say this is equal to, this n is just chilling here, so I'm going to keep plopping them down. I want to expand this. I want to expand this n factorial the same exact way I just did. So I'm going to say n times n minus 1, and I'm going to strategically stop on n minus 2, and maybe you can see why. Down in the denominator, we have 2 factorial, which is 2 times 1, and that's just 2. Why would I strategically stop on n minus 2 factorial here? Well, look at this. I have n minus 2 factorial over n minus 2 factorial. Even if you know nothing about factorial logic, you know that anything over itself other than 1 is, or other than 0 is just 1. So with that said, I can cancel these n minus 2 factorials. I now have n plus, and I can factor this in if I want to. I can say n squared minus n all over 2. Okay, cool. In order to add two fractions, or rather in order to add something that has a fraction, I need the common denominators. So actually I'm going to do this. I'm going to sneak a 2 over 2 here, right? Because 2 divided by 2 is just 1. It's the same thing as just 1n here. I now have common denominators. I can add across the top. I end up getting n squared plus, well, it's 2n minus n, so 2 minus 1 is 1, plus n all over 2. This is equal to, let's factor out the n now. I'm going to have n times n plus 1 all over 2. Interesting. Let's go to this case. We have n plus 1 objects, and we're selecting 2 of them without replacement. So just going to use the formula here. Same story. Up top, I'm going to have an n plus 1 all factorial, though. And this is going to be all over 2 factorial times, so let's see, using the formula here, it's going to be n minus r, so n plus 1 minus 2. I guess I can write all of it. N plus 1 minus 2. Hopefully I have the room. Factorial. Cool. All right, I know that n plus 1, I think I might need the room here, so no, we're going to risk it. So let's just simply do the simplification here. I know that this is n plus 1 factorial. This is not changing. 2 factorial is just 2, so at least we can make use of this middle step a little bit more. 2 times 1 is just 2. And here, this is going to be 1 minus 2 is negative 1, so n minus 1 factorial here. And hopefully you're seeing a very similar kind of idea can be applied from the last case. N plus 1 factorial I can expand as n plus 1 times, if I take away 1, I just get actually a normal n. And then times n minus 1 factorial, and I want to stop it there for that same exact reason I did before. I have that n minus 1 factorial, which cancels with this n minus 1 factorial, bringing you to n plus 1 times n. This is the same as this. It looks like these two match, which is kind of cool. So my conjecture is that this guy will match as well. Let's do it. If I use this new formula here, so I'm going to use the replacement formula this time around, it looks like it's going to be n plus 2 minus 1 all factorial. And this is all going to be over 2 factorial again. We had that 2 factorial every single time. And then now it's going to be n minus 1 factorial down below. My n here is just normal n, so this will just be n minus 1. Okay, cool. All right, simplification time. Up in the numerator, 2 minus 1 is just 1, so I have n plus 1 all factorial. This is going to be over 2 factorial is just 2. And n minus 1 factorial, I'm just going to rewrite. Almost done. Lastly, I can expand this numerator, right? I can do the same exact line of thought. N plus 1 times n minus 1 all factorial. I see here that this n minus 1 factorial will cancel out with this other n minus 1 factorial, bringing you to, I'll put this n up in front because that's the preferred way. I have n times n plus 1 all over 2. It's the same exact result as the other two cases. And if it helps you, I can write this as n times n plus 1 over 2 as well. It's the same thing. So hopefully you guys see what I see. This is the formula, the expression for triangular numbers. If I go back here, this is what we talked about at the very beginning. What did I start this whole video with? I did 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. Yeah, well, you can generalize that as 1 plus 2 plus 3 plus da-da-da-da-da to n. You get the expression for triangular numbers. And also look at this. They even kind of hinted at method number 2 here of mine. N plus 1 choose 2 is the same exact thing, just different notation as n plus 1 choose 2. So that's already by definition of triangular numbers, method 2 here. The kind of newer aspect of this, in my opinion, for me at least, was connecting this to 1 and 3 as well. And it's fun to use a game like TFT as a vessel to explore that. So that's all I have for you in this video. I'm going to ask you to continue to math on, and I will do the same. I'll see you in the next video.